This is just a quick simulation to show you what we were just talking about and how Faraday's law works. We've got a magnet here that we can move, and if you move it fairly slowly, you can watch the voltmeter here at the top. So if I move it slowly, I get some voltage, but if I move it faster, notice I can actually peg the voltmeter here, so I can make it go fast enough. So what I'm doing, of course, is I'm increasing the magnetic field. As I bring this north pole closer in, then I've got more magnetic field. Of course, when it's just sitting there, the flux is the same, right? So I need to have a moving magnet to change the flux through this coil of wire. If there's a voltage across this coil of wire, then I can have current that makes the light bulb light. And if I change the direction, then what happens is the current initially flows the other way. So you have to play with this a little carefully, but if you have this north pole coming towards it, notice as I move towards the bulb, it goes negative, and then as I go away, it goes the other direction. If I change it, it's going to go positive first, and then if I stop, it'll go to 0. If I pull away, it'll go negative. So it determine the direction we're going to get to next, but I wanted you to at least see this, that if nothing is moving, we don't generate a voltage. What we have to do is have a moving magnet. And then we generate a voltage, which if we've got a complete circuit, we can then have current flowing. And it's understanding this current flowing that's actually going to tell us about the direction. So the direction comes from Lenz's law. And it's often written as the induced EMF, the induced voltage, is equal to minus the change in the magnetic flux with respect to time. But the sign convention can be a little bit tricky. So the way I tend to do it is I say the absolute value of the EMF is equal to this, the absolute value of the change, and then I find my direction by doing the analysis of what opposes change. Because what happens is, as this magnetic field, if we go along this previous example where we had an increasing magnetic field, what happens is we get a current. So if this is a conductor, we get a current to oppose the change. So we've got two options, really. I can think about my loop. I could have a current that goes this way, right? Or I could have a current that goes this way. And so let's think about what magnetic field you would get inside, what flux you would get generated from its own current. So if I have a current loop like this, I hope you can convince yourself by using your right-hand rule that in fact your magnetic field is going to be going like that. In other words, we can take our, if you remember our right-hand rule, you can take your thumb in the direction of current, then your right hand tells you, hey, that magnetic field circles around in that way. So if I do this, if I put my thumb right along here, right, my thumb right along there, then I figure out where my fingers curl on the inside, then that gives me up, okay? It gives me sort of out of the page. And just to make sure, my magnetic field, if I put my thumb in this direction, so my thumb is in the direction going clockwise, then I get, not surprisingly, magnetic field into the page, okay? So into the page, and this is out of the page. This is just looking at the inside. Of course, with a loop like this, if I have a current going like this, my magnetic field is really coming out and going back like this, right? So this is the magnetic field coming out of the page and then coming back in, okay? So if I have current going this way, this is my magnetic field. Okay, so what I want to do is say, let's say I've got an external magnetic field and it's just turning on. Okay, so here's my loop. And it's not connected up to anything that gives it current. It's just a wire. So it's just wire sitting by itself, minding its own business. And then we have a magnetic field that slowly starts to turn on. So these blue dots are my magnetic field from something else. Okay? It could be, like in the simulation, I'm bringing up a magnet in that area. Okay, so I'm turning this magnetic field on. And what this orange loop says, it says, I don't like that. I don't want it. That's not the way I was. I like the status quo. I don't like change. And so what it wants to do is it wants to induce, and I'm going to draw these with circles around them, it wants to induce something to oppose the change. And since it's seeing bigger and bigger arrows coming out of the page, or bigger and bigger dots if you like, it wants to oppose these dots, which is the change in flux. And so it opposes these dots by inducing the opposite, right? And it says, hey, so these are my induced. And so the X's are induced. Induced magnetic field to try to stop the change from happening. So as this magnetic field grows and grows, at the 1 second mark, it gets to 3 millitesla, it says, hey, I didn't want it that big. I wanted it small, so I'm going to send a magnetic field the other way so my flux can be closer to what it was before. So it opposes the change of flux. So it induces a magnetic field, which means to get X's, I have to have a current going this direction. Okay, so that's the current that gets set up. And so from that, that's how we find our directions. Really going to focus on our direction associated with the current. And so that means that we have a voltage difference that pushes this current in that direction. Okay? It's like it was set up, I mean, there's not a battery here, but it's like it was set up with a battery like that, right? Because that's what gives me a current like that. So you can think of that as my induced voltage, but it's easier to think of it in terms of then the current that gets set up to give you a magnetic field to oppose the change. Suppose we look at the same situation. The magnetic field was on, and for some reason, and it's due to something, and it's let's say it's set. It's just on and it's steady. So it's at, let's say, 10 millitesla, and it's constant. Well, if it's constant, there's no current, right? No induced current. It's like when the magnet is just sitting in the middle of that coil. There's no induced current. But let's say something turns it off. So this gets turned off, and maybe it goes slowly, but it starts to reduce down. So this gets turned off. Well, if that's the case, then all of a sudden, we get an induced current that says, hey, I don't want to lose those dots. So we induce a current to create dots, to sort of save, if you like, save the situation, save the status quo. It wants things to stay the same and wants to oppose change. So if I have dots, then what that means is I'm going to have a current that's going to get induced in that direction. Okay? So the direction that the induced current happens is that the induced current creates a magnetic field that's induced. So I'll have a circle around it when I draw it. the circle around the dots or the circle around the X's. Those are the induced magnetic fields. So the induced current creates an induced magnetic field that opposes the change in the flux. So if we're seeing a flux that has a bigger magnetic field, say out of the page, then it says, wait, I've got to create a magnetic field that's into the page to balance it out. If it's a magnetic field that was out of the page and it starts to drop, it says, hey, wait, I need that out of the page induced magnetic field. So this is how we decide the direction. This is all Lenz's law that tells us that this is how it sets up to oppose the change. And what that means is that it makes it harder to do something. It sort of creates some resistance, if you like. If we have a loop like this and we're bringing a magnetic field in, it kind of makes sense that we induce, so if this is moving this direction, then what happens is we induce, so our field lines are getting stronger this way, so it induces a magnetic field. The induced magnetic field would be kind of pointing in that direction. That would be the induced field. I'm going to make a circle somehow on it. And it would oppose the change. So that would actually feel like a force as you're trying to bring this magnet towards this loop. It actually repels it as we go along, right? So because it's creating a little tiny North Pole situation, right? A little bar magnet kind of setup. So it actually opposes the change. So that's another way you can think about it. You get a force here, force that opposes the change. And it gets harder to move it faster. You actually need more energy to move it faster.